Hey guys, so this video is going to be going over heating and cooling curves, basically a review of what you saw in the lab, why you saw what you saw, and what it all means. So we're going to start this, what I have on the screen here is my graph that I made when I did the lab. You can see that I was able to get some negative values down here at the bottom. I had some steady no temperature change here, and then around 10 minutes that temperature increased. I'm going to make some lines on here because I thought that this change in direction was pretty peculiar, and I wanted to kind of isolate that as well as that change in direction. So we know that when we were doing the lab, we had a constant source of energy, a constant source of heat. The hot plate was giving energy to the beaker. And we didn't take it off the hot plate. We didn't turn it down. We didn't do anything like that. So why are we seeing these changes in the shape of the graph when it had a constant heat source? So first we need to ask ourselves what was happening. I'm actually going to draw one more line right here because it looks like it was going up, it went flat, up, and then flat. So I see sort of a pattern here. So what was happening from like 2 minutes to 10 minutes? If you recall, what you saw in the lab was that this was the period of time when the sample was melting. So we had liquid or solid ice melting to liquid water. So I'm just going to write on here, we had solid, oops, that's not the color I wanted, hang on. We had solid changing to a liquid. And so that's what that was a phase change, right? And then once we hit that black line, that 10-minute mark, then all of the solid was gone. The temperature started to increase again. So right here, we had just liquid. And then think again, once we got that next plateau, what did you see happening? Well, hopefully you're saying to yourself, oh, it was boiling. It started to boil. So once again, we saw another phase change where it was going from liquid to a gas. So if we're looking at patterns here, I can see that whenever there's a plateau, whenever the slope is zero and it's a flat line, that's when we have a phase change. So I'm going to type that in over here. So plateau, oh, that's big. That's really big. That's okay. Plateau equals a phase change. Okay. So we know that because we can see it. And the question now, I guess, is why? Well, when we had the liquid, so like from 10 minutes to 17 minutes, the liquid was heating up. The temperature was increasing. Remember, we have over here temperature in degrees Celsius. So at this interval, the temperature was going up, which makes sense. There was energy going into the system. The heat, the hot plate was on. Makes sense that the temperature would increase, right? So in order to understand what was happening at the plateaus, we need to understand what the energy was being stored as here during this increase interval. And if you recall, we had 3 types of energy storage. One of them was chemical. We're not going to get into that yet because there was no chemical changes here. We were just melting ice. So then the other one that has to do with heat is that thermal energy. So I'm going to write ETH right here. And if you have your reading still or your notes, thermal energy is energy that's stored as particle movement. And that makes sense here because the particles are moving faster. Remember, oh, here's some orange. So actually, I guess I can do that green. So thermal energy, we say, is the same as kinetic energy because it's movement. It's those particles moving. And on that graph, we see the kinetic energy is increasing. Well, how do I know that? Because the temperature is increasing, and temperature is average kinetic energy. Okay, and that's, what did I just say? Temperature. And then, of course, all of those are movement. Okay, so thermal energy, kinetic energy, temperature, movement, all of those are increasing. All of those are the same. thermal energy is kind of like the storage. It's what all of those things are going into. Oh gosh, I'm gonna sneeze. Okay, so now the question is, what is that energy doing from here? Let me just letter these to make it easier to talk about. So A, B, and C. So from B to C, the heat going into the system is causing those molecules to move faster. So what the heck is the heat doing from A to B and from C forward? It doesn't make sense that heat's going into it, but the temperature is not increasing. So we need to think about what's happening to the particles themselves. When we have a solid, the particles are close together, really close together in a nice lattice structure, and they're vibrating in place. So they're vibrating. In order to make them change state, say from a solid to a liquid, we need to increase the distance. We need to pull them apart. And that's not easy to do. It takes energy. It requires energy. So instead of increasing the temperature, the heat going into the system is pulling those particles apart, causing the distance between them to increase because they can't move any faster until there's enough room for them to do so. So I'm going to put right here, we have energy going into the system as phase energy. Because phase energy is energy due to the arrangement of the particles. And from A to B, the arrangement is changing. It's going from a solid, they're close together, they're vibrating. And then when they're a liquid, they're pulling apart. So from A to B, we have these particles being pulled apart. You'll notice that right here, there is a slight temperature increase before that ice is gone. But remember, it's not a perfect setup. Our thermometer, if it was in the sample, this part of the thermometer at the bottom is going to be warmer than the top part. And if there's only tiny little ice, up here at the top, well, that's not going to give us an accurate temperature reading of the entire sample. So the temperature can't go above 0 until all of the ice is gone. It's the melting point. Therefore, if you go above that, you're past the melting point. Therefore, it has to be melted. So the temperature stays 0 until all of the ice is gone or until the thermometer can't read it anymore. And then that temperature starts to go up. So now that these particles are a liquid, particles move like this. They're liquid, but they're increasing in temperature. So they're moving faster until they're like, hey guys, wait, I want to move faster, but there's not enough room. You're all too close to me, so we need to spread out. So they're like, okay, energy, stop making us move faster, start pulling us apart. So now the speed from C forward is constant. The velocity, the temperature, it's all constant. What's changing is the distance between them. So here we have these liquid molecules and they're being pulled apart so that they can be a gas. And remember, gases are free to move all over the places as much as they want to. So again, right here, we have phase energy. And that's that. So what I need you guys to know, what I need you to be able to ask yourself and answer are questions like this. Where do I see a phase change? Where is all liquid? Where is all solid? Where's all gas? At what intervals are there two phases of matter present? Solid and liquid or liquid and gas. At what point is the temperature increasing? At what point is the temperature constant? Why do the plateaus happen? Remember, in order to answer that, you need to know what the energy is busy doing instead of increasing the temperature. And then here, this is a really awesome diagram because it tells you the states of matter. It shows you that shape, and it also has these particle diagrams, which I really love because you can see the structure of them. They're close together in a solid. Then we have some close together, some in a liquid, all liquid, liquid gas, and then all gas. And I think that's a really great visual to add to this. So feel free to go back and pause the video or take a look at those graphs, whatever it is you need to do. Keep these things in mind, and you should be good. Thank you.